Hi, my name is David Cermak, and this is my presentation about IPv6 networks and microcontrollers, or ESP32 specifically. So this presentation is trying to elaborate on the two questions below. What would happen if we take ESP32 and put it inside IPv6 only network, and also if we could just switch off IPv4 completely on ESP32. So a few notes about myself. I am an embedded developer working in embedded field for my probably entire life. But for the past 2 years, I've been working for expressive systems, so mainly playing with ESP32 and other expressive chips. I also like to play with Linux network and Linux networking interfaces, and I'd like to connect networks together, use network interfaces for debugging and for connecting embedded devices and debugging microcontroller network stacks. So that was about me, and now about the talk. So here are actually 5 topics that I'm going to talk about. The first one is a, let's say, very introductory topic about IoT and what IPv6 means for IoT. The second topic, IPv6 modes in lwIP. So lwIP, or lightweight IP, is a network stack which is used on expressive devices, and not only on expressive devices. This is probably widely used on many other embedded devices, usually those devices that cannot run any advanced operating system. So this section is, and also the other section, these two sections are perfectly applicable for any such microcontrollers or any such device that use this TCP/IP stack. Section number 3, network interfaces in lwIP. This section will mainly focus on runtime configuration of this stack. Section number 4, comparing resources on ESP32. So here I would like to show differences between binaries for ESP32 if it is compiled with a dual stack, or IPv4 only, or IPv6 only. And the last point, probably the most interesting one, is about ESP32 demonstration of ESP32 running in QEMU and connecting to IPv6 only network. So let's move on to the first topic, IPv6 and IoT. So having a global address is a great benefit for IoT device, because we actually we don't need any service, any third party provider to connect to that device, because this device is available from any place on the internet. So we don't need no broker, gateway, or anything like that. But on the other hand, this device is exposed to all the threats that internet has. So from the perspective of expressive engineer, I could say that our customers usually prefer IPv4, and there is no real demand for IPv6. And the reason is the main reason is security. Because if they use some big cloud provider, some service, connectivity service, they have some security by default. But if they want to connect directly over IPv6 global address, they would have to implement everything on their own, and there is no default security. The second point, what I would like to highlight here is that maybe for those who have played with IPv6 and ESP-IDF, you already know that everything works, that as ESP32 is able to receive global IPv6 address, and everything works. So what's my message here? Although everything works, not everything would work on IPv6 only network. So that's my first message. And the second message is focus on really small devices. So IPv6 doesn't only mean that we have a global address and availability and some different routing mechanisms, but mainly this focus on embedded devices and smaller embedded devices. There are some major optimization on the local network, which is probably very beneficial for those smaller devices. So first of all, on this for these small devices, we are very concerned about the resources. So if we could save a couple of kilobytes on a network stack which we don't use, that's a big benefit. The second point, we usually also focus on performance and low power. So in terms of local networking, the IPv6, as I mentioned, has some benefits. It replaces this ARP protocol. Broadcasts are replaced with multicast. So the device, the small device, can sleep quietly, can save power, and only respond to multicasts and actually remain in the sleep mode if the message is not for the device itself. The last point, we also, and this is probably the most important point for embedded devices, we usually focus on startup, connection, and repeatability. So receiving an IP address in the beginning of starting embedded application is essential for embedded devices and for most of the embedded applications. So the device could start doing some housekeeping task without an IP address, because typically if the device is to receive an IP address from the HCP server, it takes some time. But for IPv6, we could get a let's say local link address, and if we know that inside this local network there is no need for collision detection, we can simply switch off this duplicate address protocol, and we could immediately get a valid IPv6 address, and this address would be the same for repeatably the same for all the time. So this is really a big benefit for most of the embedded applications. So let's move on to the second point, IPv6 mode supported in lwIP. So here we know that IPv6 configuration could be either stateless using auto configuration process. So the service would provide just the prefix and the device would calculate and provide the rest of the address, or stateful, so managed service by the HCP version 6 server. So we look at the configuration of lwIP. we have this configuration value which is enabled by default. So in lwIP we have this stateless address auto configuration enabled. On ESP-IDF this configuration option is actually controllable from project configuration menu. So we can, if we want to use it, we have to specifically enable it because in IDF this option is disabled by default. DHCP version 6 is available in lwIP. You can see that this configuration option is disabled by default, but could be easily enabled. If we look further for other DHCP version 6 configuration, we can see these two options, stateless and stateful. But please notice that the stateful configuration is not supported yet. So this is a very important note for all lwIP devices. We simply do not support DHCP version 6 stateful configuration. There are other configuration options that we can check following the link in the presentation. Most of them we just leave by default. One interesting is this duplicate detect attempts. So as I said before, if we are sure that there would be no collision inside a local network, we can just set it to 0, and then we get immediately a valid local link address, which might be useful in some embedded applications. Well, all this IPv6 configuration is perfectly okay for IPv6 networks, but might not be 100% correct for IPv6 only network. And for this IPv6 only, we need to configure some other stuff, which is typically DNS servers. So how do we do that? This is not supported in ESP-IDF. There is no configuration options to enable that. But in lwIP, we have actually two options how to get the DNS information into the system. So first one is using an NDP, Neighbor Discovery Protocol. So we could use the router advertisement daemon to provide the recursive DNS entry. And the other option is to use the DHCP version 6 in the stateless configuration. And for that we need to enable the flag which is called the other flag. And I will show it in the demonstration later. So this was about as I say, the compile time configuration, and now let's move on to network interfaces in lwIP. So mainly the runtime configuration. So in lwIP we have these network interfaces which are probably available in any TCP/IP stack, but on these network interfaces we can specifically enable or disable some configuration, which is actually very useful. For expressive chips, we usually have at least these three interfaces on one chip. So we can have Wi-Fi station, and on the same device we can have Wi-Fi access point and Ethernet, which is on ESP32 only, and we can have some other interfaces and connect to network over UART or SPI or any other communication media, but usually we have these three. Duplicate interface, that's interesting point, which we can typically have on ESP32 if we connect the device to over Ethernet and Wi-Fi and connect to the same network, which is a pretty common problem. And in this case, we need to be aware of having two IPv6 addresses. So we need to configure each network interface separately, and it might be useful to enable global addressing on one interface and disable it on another. So for the auto configuration, we have this runtime configuration option called IP6 autoconfig enabled, which is actually a runtime configuration which we can modify during runtime. And as you can see here, this is a section from our lwIP modification on esp-idf. So if we have the global auto configuration enabled in the project configuration menu, it's automatically enabled for all network interfaces. Another runtime configuration is the DHCP version 6 stateless. So we have an API to enable DHCP version 6. Again, this configuration is on network interface level, so we can enable the DHCP version 6 separately for each interface, or only to those interfaces which we like. All right, so let's go to the next section about comparing resources on ESP32. As I mentioned before, we would just like to compare what memory footprint we get if we compile with IPv4 only, IPv6 only, and dual stack. So esp-idf provides this idf underscore size, which could simply compare map files and div them. So this is a IPv4 only versus dual stack. So actually, please notice this the last column called difference. So you can see that if we disable IPv6 here, we save over about 1 kilobyte in flash, which is probably a negligible portion at this point. A bit more interesting numbers we get if we compare IPv6 only versus dual stack. So looking at the last column, we save almost 30 kilobytes in flash, which looks like a big number, but we usually have enough flash memory. What is more important at this point is that switching IPv4 off, we save about 600 bytes in RAM in the data section, which is a small number, but for embedded engineer it really means something. And for ESP32 developer, every expressive developer knows that actually every byte counts if we are talking about RAM data section. So if we put these numbers into a table and display like a comparison or chart, we can just display the percentage difference for the data section, for the flash data section and flash code section. So the big numbers or bigger bars are for IPv6 only. So we can see that really the IPv4 stack is quite big, and switching it off, we would save between around 3%. But if we switch IPv6 stack, then the savings is really negligible. So it's below 1%. All right, that was all from this presentation part, and now let's move on to the demonstration section. I've prepared this this environment so that we can connect the two containers, one running QEMU or ESP32 in QEMU to the other container which runs some network utilities which we typically use for configuring IPv6 networks. You can check all those examples on these on GitHub, cloning this repository, and so let's switch over to the demonstration mode. So this is the example I have prepared and posted on GitHub so that you can clone it and check it out yourself. So it also contains a README file about the complete configuration of my setup, so you can easily run it inside the containers. So this is the setup, and this is how we configure the QEMU container. We need to run it with the network admin capabilities. We also need to start QEMU inside the container. We start the QEMU with with this ESP32 mode, and also in this TAP mode, TAP networking mode. This is very important, and because of that we need to create a TAP interface inside the container and bridge it together to the default Ethernet 0 container. This is the other container which just contains the packages for router advertisement and DHCP. We also want to bridge the containers together, and we need to, of course, set up IPv6 and all that we need. For all that we need network admin capabilities. Well, this was about the configuration of the environment, and now about those examples. So here is the source code of the example. It does nothing but initializes and starts MQTT client trying to connect to this server. And it also tries to get the DNS information from the TCP IP stack and prints the IPv6 address of this server. I said it's just one example, but it runs in 3 different configurations. So this is how the configuration is set up for the example. And now let me open it in project configuration menu. So this is the standard menu config, and if we go into example configuration, we will open actually this this submenu where we can set up MQTT broker address. But what's more important are these configuration modes of IPv6. The first one is the default one, which is actually enabled by default, is the IPv6 global autoconfig. So this is the one that would work correctly for most of the IPv6 network, but might not work for IPv6 only network. So for that, we have the other configuration options, which we need to set up other parameters of the network, and this is actually the DNS server, which we can set up using router advertisement or DHCP version 6 using this other flag configuration. I'm going to show it a little bit later. Now let me also quickly go to the component configuration and lwIP, and we can look at the configuration option which is used to enable this default IPv6 connectivity. So this is how is it called: enable IPv6 stateless address auto configuration. All right. So now let's go back to the example and to the source code, and let's look at these configuration options for lwIP. So this is actually the configuration, the default configuration file for lwIP, including the documentation for all these configuration options in the commands that are then used to generate lwIP documentation. And this is lwIP options which are set from esp-idf. So we can either set some options using 1 or 0 or whatever value we need, or we can set it up based on some configuration options which we typically set using project configuration menu. So most of these options which expressive things, expressive thing that users would like to configure or would need to configure, have these configuration option which can be configured from menu config. This is true for the global autoconfig, but not for this one, and not for the other one with DHCP6. For that, we have to work this around using this thing. Well, we can possibly just hard code it here, set it in lwIP options, but that's not the preferred way, because in that case we would simply modify the framework. So here is the make file for this example, for this project, and using this target compile definition, we can actually force some lwIP flags to be preset to some certain value. So if we set the HCP other flag from the example configuration menu, then we set also this lwIP DHCP to on. The same way is for the router advertisement recursive DNS server. We set this maximum number of DNS servers to 1, because by default it's 0. So let me switch to, oh sorry, oh, yeah, let me switch to the screen where we have the containers running. So the left hand side we have the QEMU container, and we now can start the QEMU with the in the default configuration. So running the IPv6 global address in the tab mode, and in this case we should get IPv6 address by default. Yeah, so starting the ESP32, and let's switch to the other side and start router advertisement daemon, and we can see correctly that we have received not only the local link address but this time also the global address. Getting the DNS information succeeded, but the IP type is not version 6. So these are the addresses which we received, and with these addresses we can connect to any place, but for IPv6 only address we have no way to get DNS server, so to resolve DNS addresses. Now we can switch over to the other example, to the other configuration, which is getting the DNS server from router advertisement daemon. Yeah, but before starting that, let's move on to the configuration of this router advertisement, and okay, let's see, configuration, open the configuration, and let's look at the configuration here. Before we configure that, let's first of all highlight these two flags, which are very important. So first one, advanced manage flag is off, and the second is the other config flag is on. So the other config flag actually, yeah, this managed config flag must be off, because we don't use stateful configuration. We don't have DHCP version 6 server, but the other config flag needs to be also off. We'll show that later, because we have this DNS server set up here in the router advertisement service. Yeah. And this is probably all what we need to do with this configuration. Let's start the service, and let's also start the ESP32, and let's see what is going to happen. Yeah, we see the debug message that the DNS server was the address was acquired, and we see this debug message as well, that the DNS information not only succeeded, but we also got the IPv6 address of the DNS server. So let's quit the router advertisement daemon and open up the configuration again, because this time we need to set this other configuration flag on and remove the DNS configuration from here, which actually says that the DNS configuration will be provided by the DHCP version 6. And now on the other side, we just open up a container. Well, start the binary with DHCP version 6. And this time we have also enabled the DHCP 6 debug information, so that you can see all these messages, and yeah, about different states of DHCP, and you can also see that this time also the getting DNS information succeeded, and the type of the DNS server address is 6, and this is the address that we got. So let's also quickly switch to the other container, and let's display the configuration of DHCP version 6. Yes, and yeah, this is actually the configuration value of those name servers. So you can see 25 and 25. So we got the same address that was configured. So this way we are able to set up other configuration values to ESP32 network stack. So either using router advertisement or DHCP version 6 file, configuration file. So this was the first example of running ESP32 inside a container and connecting to the other container where we have network utilities. What we need to do if we want to connect to IPv4 address. So typically on this right hand side container, we just add some network translation, network address translation service. So NAT64 and DNS64 to provide this translation and connect this netutils container to IPv4 world or to dual stack world, so that we can also access IPv4 addresses. We can run some well-known service for this translation, for example, Joule or I think Taiga also. But we can also set up a new tunnel interface and implement the address translation on our own. But what we can also do, and this is probably another one other of my example, we can replace this network address translation container with a real device, which would be ESP32, because ESP32 actually and ESP32S2 has also these two network interfaces by default. So we can have access point and station Wi-Fi mode. So the station would connect to the outside world running dual stack. So it would receive also IPv4 address and IPv6 address, and it could provide this network address translation, and the internal network inside this this access point would be IPv6 only. So this would be another example, and just for curiosity, I have prepared a very simple demonstration of very work in progress version of this setup. What's very important is that this setup is actually what we really want to achieve for embedded devices, for the internal network, which is created just for embedded devices, and then so that we don't have to care about network address duplication. So we could switch off this protocol, and startup time would with valid IP address would start. We can use local addresses only inside this simple subnet, and the outside world connectivity would be provided by the root node. So this setup very much resembles the setup of ESP mesh, so that we could have multiple devices connected to this access point, and having a root node running a dual stack, and all other mesh nodes could just simply run IPv6 only stack, and using local link addresses and running skipping this network address duplication. So uptime and repeatability of addresses would be perfect. So let's quickly look at those examples. So let me just quickly show the other example. So this runs on real physical chips. I have two devices connected to my machine. So this one, this terminal actually shows the STD out of the gateway ESP32. So the one that runs to interfaces, and at this point it only produces this debugging messages that access point interface received some data, station received some data, and in case access point receives some IPv6 data, it tries to apply very simple network translation and recalculate the IPv4 header and send the data over to Wi-Fi station. So if I switch back to the other terminal, which is connected to the other ESP32, which actually runs very similar example as the one I've shown before, with which run inside QEMU. But the difference is that this example runs IPv6 only, so there is no IPv4 implementation at all inside these network stacks. It really just connects to this internal network which is created by the expressive device, by ESP32 access point, and connects to it and tries to connect to IPv6 address, which is then translated into IPv4, and the packets are sent over. So this is the other terminal, and here we can see that we received only IPv6 addresses, and at the same time we received only local link addresses. So I also switched this address duplication detection, so we get the IPv6 address really quickly, and always the same address, and this device after the startup just tries to connect to this server using MQTT client, and as you can see, this address is also a local link address, and it corresponds to the access point network interface of the other device. So this is all I wanted to show you, and let me switch to the presentation again for a quick recap. So as a word of summary, let me just recap what what we have been talking about. IPv6 is supported by default on ESP32 and on ESP32S2. For IPv6 only, we might need some adjustments, which we have shown during the demonstration. And if we are running some embedded application on a microcontroller, we can look at other features which IPv6 provides to save some energy, memory, or performance. So this is all from me. Thank you for your attention. Please use IPv6 on microcontrollers, but also be careful because security doesn't come in by default. Thank you. Goodbye.